Hello and welcome back to the next section in our Introduction to Space Exploration. In the last section, we learned where space begins and how we define space. We know more about the size of Earth, the solar system, galaxy, and universe, as well as the distances between Earth and the other planets. In this lesson, we'll move on to the space environment and how its challenges affect every part of planning a space mission. After we understand the key aspects of the space environment, we'll get into the human element of living and working in space. But first, let's get started on our topic for today, the space environment and spacecraft. You've learned from leadership and team building experiences that understanding the risks of any situation and planning for those risks will make your chances for mission success much greater. Even though space is just an hour's drive straight up, the environment is very different from our environment here on Earth. In fact, just about everything is different. We'll look at the basic challenges of the space environment while emphasizing gravity, atmosphere, vacuum, micrometeoroids and space junk, radiation, and charged particles. The reason we care so much about the space environment is that it has a devastating effect on people and the spacecraft, including electronics, solar arrays, storage batteries, paints, and blankets. Yes, spacecraft have blankets, but not the kind you're thinking about. Spacecraft blankets are multi-layer insulation which keep the spacecraft at the right temperature. By understanding risks from the space environment, we can design and operate our spacecraft, protect the crew, and improve our chances for success. Let's talk about the elements of the space environment as shown here. We design and build spacecraft within a protected environment here on Earth, which can take many years. But we hurl the craft into orbit abruptly by taking about 10 to 12 minutes to get from Earth's surface. The spacecraft finds itself in a very hazardous environment for the rest of its mission lifetime, which typically is 5 to 15 years. You can see the spacecraft here within the space environment with gravity, atmosphere, the vacuum of space, micrometeoroids and space junk, electromagnetic radiation, and charged particles all exercising their own influence on the spacecraft. Oh, by the way, several people may be on board. So what have we gotten ourselves into? Let's discuss each part of the space environment and understand what's happening. We've heard the term zero gravity and even seen videos of astronauts trying to catch things that were floating in it. But the term zero gravity is not correct. Let's try to understand the gravity of this situation. As you sit in your chair, you can feel the chair holding you up by fighting the force of gravity so you can be comfortable. If your chair had legs that were 60 miles long, you'd be sitting in space and the pull of gravity would be about 90% of the gravity at sea level. You would not be floating around, you'd be sitting still, like here on Earth, and you'd feel the chair pushing up on your bottom. Of course, a chair with legs this long isn't practical, but you get the idea. So, if the gravity acting on people and the spacecraft in orbit is about the same as gravity on Earth's surface, why do these people and other objects seem to be floating around? Well, spacecraft don't just sit in one place in space, they are in orbit and are falling around Earth. In fact, the spacecraft is in free fall. If you've ever been in an airplane that's bouncing around or on a roller coaster, you may have experienced free fall. Do you remember feeling yourself lifting off the seat and having the seat belt or restraint holding you in? You'd have a similar feeling if you were falling around Earth in a spacecraft. The spacecraft and you would be in free fall around Earth. Spacecraft and everything in them, especially things not tied down, experience free fall continuously. Here's an example of how things work differently in this free fall environment. On Earth, if you needed to use the toilet, you'd go to the bathroom, sit on the toilet, and do your duty. You'd flush the toilet and everything would go down the drain. Well, It's not so simple in free fall. First, if you tried to sit on a toilet in orbit, you'd float away. Hanging on or using some sort of restraint so you don't float away and miss the toilet bowl is mandatory. Second, in a toilet on Earth, the water in the toilet bowl is held in place by gravity. The same kind of toilet in space would have the water floating around. In fact, anything you put into the toilet would float around. And to make matters worse, if you flush the toilet, everything in the toilet bowl would end up all over you. So, toilets are designed differently for space, and yes, crew members have to spend hours learning how to operate them. We know that gravity on Earth limits our ability to mix certain materials together. For example, when we try to mix water and rocks together, what happens? You're right. Gravity pulls the rocks to the bottom and they don't mix with the water. But in free fall, what happens to the mixture of rocks and water? Yes, the rocks are in free fall with the water, so the rocks don't fall to the bottom. The free fall environment allows us to mix things differently and makes it possible for us to produce alloys, life-saving drugs, and many other things that can benefit us. Here you can see some very fortunate astronauts in the Vomit Comet. The Vomit Comet is the nickname for the NASA aircraft used to train astronauts in a nearly weightless environment. The aircraft flies in a trajectory that provides a brief, several-minute-long free-fall environment. The astronauts can get used to the free-fall environment and even conduct research before carrying out experiments on board the shuttle. Can you guess why astronauts named this aircraft the Vomit Comet? You're right. To solve problems caused by free fall, nations can work together and learn from each other, as the story I'm about to tell you shows. When our early astronauts and cosmonauts first went into space, they had to write information on paper to record, calculate, and solve problems. They quickly discovered that in a free fall environment, the ink in a pen wouldn't flow out the tip like it does on Earth. Have you ever tried to write with a normal pen upside down? That's similar to what crew members were facing in space. NASA scientists developed a high-tech space pen that would pump ink through the tip of the pen regardless of its position. The Russian cosmonauts who had the same problem decided to use a simple and cheap solution. They used a pencil. However, it was discovered the pencil gave off minute fragments of graphite that could harm the spacecraft, so we arrived at a compromise between the space pen and the pencil. Now that we've discussed gravity and freefall, let's talk about another part of the space environment. The space shuttle and many other spacecraft operate in low Earth orbit, where there's still a small amount of atmosphere. The atmosphere in low Earth orbit is made up of a small amount of molecules or particles, much less than the atmosphere on Earth's surface. These molecules hitting the speeding spacecraft impart a force on the spacecraft called drag and steals energy from the orbit. On Earth, imagine you're a passenger in a car driving down the freeway. You open the window and stick your arm out the window, holding your palm so the wind, which is made up of molecules, forces your hand backward. This is the force of drag. The force of drag on the spacecraft depends on many things, including how closely the molecules or particles are packed together. The higher a spacecraft is above the surface, the less dense the atmosphere and the lower the drag force. So what does this mean? It means drag can shorten a spacecraft's orbit life by taking energy from the orbit and shrinking it. Over a long time, drag can force a spacecraft out of orbit. Drag also acts like brakes on the space shuttle to slow it down from about 17,100 miles per hour in orbit to landing speeds. And remember, we learned earlier that Earth's atmosphere doesn't just end abruptly. Even at a high altitude, like 375 miles, the atmosphere keeps creating drag on orbiting spacecraft because particles continue to steal energy from the orbit. Look at this artist's idea of a space vehicle when drag slows it down. The spacecraft's size, shape, speed, and position determine the amount of drag it feels as it hits particles in the atmosphere. Now let's look at another part of the atmosphere that affects the spacecraft. We've just talked about atmosphere as one of the elements of a space environment. We also know the water we drink is made up of 2 hydrogen atoms and 1 oxygen atom, or H2O. But most oxygen near Earth's surface is in the form of 2 oxygen atoms, or O2. In Earth's upper atmosphere, where space work occurs, oxygen atoms have trouble finding a partner, so they exist as O, called monatomic oxygen. This free, or monatomic oxygen, can react with many materials. That makes sense, but what does that have to do with spacecraft? The monatomic oxygen and other chemicals in the atmosphere can corrode or eat away the spacecraft surfaces, which can weaken the structure, change the coating's ability to withstand heat, and degrade the sensors. All this can put the spacecraft in serious danger. That sounds bad, but how did NASA face this challenge and solve the problem? NASA launched a long-duration exposure facility to study the environmental hazards of atomic oxygen and micrometeoroids on a spacecraft. They found that most monatomic oxygen in the upper atmosphere mixed with other oxygen molecules to form a special molecule called ozone, or O3. The ozone acts like a window shade to block harmful radiation, just like sunblock keeps ultraviolet radiation from causing sunburn or skin cancer. We've talked about oxygen, so let's move from sea level up to orbit altitude where fewer molecules or particles exist. As we get higher in space, we begin running out of molecules or atmosphere. This lack of molecules or atmosphere is known as a vacuum. The molecules in the atmosphere at sea level push on us, exerting pressure or drag. Aircraft make up for the lack of atmosphere or molecules at higher altitudes by pressurizing or pumping air into the cabin. That makes sense because a pure vacuum would contain 0 particles and have 0 pressure. But it's almost impossible to have a pure vacuum. So let's talk about a near or hard vacuum. In orbit, a spacecraft experiences nearly perfect or hard vacuum. This vacuum sucks particles and molecules out of the spacecraft. So what's the problem? Well, gases are usually trapped in materials used in the spacecraft, and when the spacecraft is placed in a vacuum, the gases escape. This process is called outgassing, and it can cloud sensors and lenses like those in the Hubble Space Telescope. Scientists can fix this problem by baking the spacecraft in a hot vacuum chamber like the one seen here before launching the spacecraft. So, now we know that space sucks materials out of the spacecraft. The next problem of being in a near vacuum is in space. The lack of an air layer can cause moving parts to bind. But what does this mean? If we took 2 flat pieces of metal and placed them together for about a year, what would happen? You're right, probably nothing. Our atmosphere provides a layer of air molecules between the 2 pieces of metal, so they would easily slide on one another. Now, if we place the same 2 pieces of flat metal together in space for a year, what could happen? The answer is not so obvious. Because there's no layer of air between the metal pieces, molecules can actually migrate from one piece to the other, and when we try to slide the pieces of metal, they may stick together. We call this process cold welding. Often, ground controllers need to unstick the parts. Spacecraft need lubricants to keep parts moving, but oil and other common ones don't work in the vacuum of space. Interestingly, graphite is a lubricant that doesn't evaporate into the near vacuum like typical oil would. We've just talked about two of the three problems caused by a near or hard vacuum on spacecraft. Now let's turn to the last, which is heat transfer or lack of it. Space is generally very cold, but the sun, heat from the Earth, and power being dissipated on the spacecraft tend to heat up spacecraft. When that happens, we do something to keep them from getting too hot for people and electronic equipment. There are three ways that we can transfer heat from our bodies. As you sit there in your chair with your elbows on the table, you're conducting heat from your body through the chair to the floor and from your elbows through the table to the floor. If there's a fan or air conditioner, air molecules are flowing over your skin, carrying heat away through convection. You're also radiating heat away from your body by electromagnetic radiation. If you hold your hand close to your cheek, you'll feel heat coming from your face. This is electromagnetic radiation. In space, the problem is that the spacecraft can't touch Earth, so conducting heat out of the spacecraft isn't possible. In addition, there are very few molecules in space, so convection doesn't work. We're left with radiation as the only way to get heat out of the spacecraft. So, let's understand how the basics of conduction, convection, and radiation remove heat from inside the spacecraft. To see how these three processes help us control heat in space, let's briefly look at each one. Objects usually have several ways to transfer heat in and out. Conduction is heat flow from one point directly to another through a conducting material. For example, a poker in a fire for any length of time conducts heat to the handle. When you look at this picture, you can see exactly how the concept works. For a spacecraft, conduction removes heat from components that are too hot and moves heat around inside the spacecraft. But conduction does not remove heat from a spacecraft. Convection is a way to move heat by circulating a medium, such as air or water, over an object. The fan inside your computer uses convection to carry heat away from the processor. Here you can see how boiling water on a stove moves heat through a fluid from the hot source to the cooler fluid on top. A spacecraft has special equipment to use convection to take heat away from components that get too hot. Since there aren't many molecules in space, convection doesn't remove heat from the spacecraft. In a spacecraft, we must bring our own molecules if we want to use convection to cool electronic equipment and people. In this case, we bring air and move it around in the space shuttle using fans. Radiation removes heat by sending out electromagnetic energy. This method doesn't require a conductor or fluid medium to carry the heat. Within a spacecraft's sealed parts, conduction or convection can move heat. But radiation is the only way to get heat into or out of a spacecraft in the vacuum of space. So, if you look at a large spacecraft like the International Space Station, you'll see large, flat panels that are intended to radiate the heat from the station into space in order to keep the ISS at the right temperature. Now, think back to our slide that showed the basic elements of a space environment. So far, we've covered gravity, atmosphere, and vacuum. Next, we'll look at micrometeoroids and space junk. Every year, more than 20,000 tons of natural debris from comets, asteroids, and meteors strike the Earth. The Earth is gaining weight at a rate of 20,000 tons per year. Globally, we launch up to 90 spacecraft each year. Each of these launches puts artificial debris into orbit, which causes increased risk to spacecraft. In fact, artificial debris, or space junk, may be more risky because it tends to occupy the same orbits as our operational spacecraft. So, who keeps track of spacecraft and debris in orbit? You're right! NORAD tracks more than 9,000 pieces of natural and artificial debris, as well as operational and non-operational spacecraft. Not only do we have old spacecraft, spacecraft parts, launch vehicles and components, but we've also left tools and gloves in orbit. Some estimates say space may hold 40,000 pieces of natural and artificial material that are golf ball sized or larger, and billions of tinier pieces. They're all too small to track, but could seriously damage spacecraft in orbit. What would happen if you were hit by a small bolt that was going over 17,000 miles per hour? Ouch! One of the earliest pieces of space junk was the glove of Gemini 4 astronaut Ed White during America's first spacewalk. You may never have thought a glove could be dangerous, but now you can see why. Even though the particles may be very small, their high velocities give the momentum and the potential to damage spacecraft. What space debris can do to a spacecraft becomes clear from two dramatic examples shown here. In 1996, a piece of launch vehicle clipped off a 6-foot section of the Ceres spacecraft. Without this section, the satellite couldn't point toward Earth. On the right, you can see where a tiny paint chip in orbit cratered the Space Shuttle Challenger's window. We learned that the sun sends out energy across the electromagnetic spectrum in the form of radio waves to X-rays and gamma rays. Energy from the visible light of the sun is useful for satellites in generating electrical power from solar cells. Infrared wavelengths of energy striking a spacecraft can heat spacecraft surfaces. This can be a good thing if it's cold, or a bad thing if it's too hot. Certain electromagnetic wavelengths, most notably ultraviolet radiation, can damage electronic components and surfaces, including solar panels. How can we solve this problem? Well, electronic components are shielded or radiation hardened to withstand the continual bombardment by damaging radiation. On Earth, we're protected from the sun's ultraviolet radiation by the atmosphere. But in orbit, there's little protection for people, so we make sure to shield ourselves from harmful radiation. The particles of electromagnetic radiation, called photons, can strike surfaces of spacecraft and, over time, can create enough force to change the spacecraft's attitude. This force is called solar pressure. The solar max, shown here, has very large surfaces like these solar panels and has to correct for pressure from solar radiation. That could change the altitude and maybe even the orbit of the spacecraft. Next, we'll look at what might be the most dangerous elements of the space environment. Charged particles that bombard the spacecraft come from the sun through the solar wind and solar flares. One of the interesting and beautiful effects of these charged particles is the aurora, or northern lights, shown here. Galactic cosmic rays are high-energy particles from old stars or spectacular events in the galaxy and beyond the solar system. They may even come from the Big Bang, which is a theory that some scientists say explains the origins of the universe. Another major source of these very dangerous charged particles is the Van Allen radiation belts. The charged particles do not originate here, but they get captured by Earth's magnetic field in two donut-shaped regions around Earth, known as the Van Allen radiation belts. In the diagram, you can see Earth surrounded by two gray areas. These are known as the inner and outer Van Allen radiation belts. These regions protect us from charged particles here on Earth, but present special hazards to spacecraft passing through them. It doesn't matter whether charged particles come from the solar wind, the Van Allen radiation belts, or the other side of the galaxy. They can harm spacecraft in three ways, which are called charging, sputtering, and single event phenomenon. Charged particles hitting the spacecraft surface can develop a small charge or voltage that can cause a shock, much like the shock you get crossing a carpeted room, and touching a doorknob. This is called spacecraft charging, and it can build up on different parts of the spacecraft. If it builds up too much, a sudden discharge or shock may damage them. You can see the effects of electromagnetic charging on a spacecraft in this dynamic photo. Charged particles hitting a spacecraft's surface can also cause sputtering, which you can think of as molecular sandblasting. The continual bombardment of surfaces by molecules can eat away at surfaces over time. Usually, sputtering is not a problem unless spacecraft are in orbit for 30 years or more. When charged particles penetrate deeply into a spacecraft, they can disrupt electronics. For example, charged particles can lock up a computer, causing it to need resetting. Or charged particles can corrupt the memory in the computer. Each disruption is called a single event phenomenon. It's difficult for us to prevent these random events, but spacecraft are built with shields to help protect them and software that allows the computer to manage the effects of charged particles. We've reached the end of this section in the Space Environment chapter. Answer the first 3 questions by reviewing the material. Make sure you have the answers right. Then, get creative and decide how you would solve the problem of space junk from an astronaut's and engineer's point of view. In summary, you've learned the hazards and challenges of the space environment and how they affect the spacecraft. You know that gravity has to be conquered to perform important research and experiments in space. You learned there's no such thing as zero gravity and spacecraft are in free fall around Earth. You understand the atmosphere can shorten orbital lifetimes and damage spacecraft surfaces. You've become familiar with the problems and solutions of the space-created vacuum. Micrometeoroids and space junk continue to be a problem in space, and you've given some thought on how you might solve this. And you know that radiation and charged particles are sources of extreme danger to a spacecraft, and you've learned some of the solutions NASA and the Department of Defense use to protect against them. We've just learned that environmental hazards posed by the space environment affect the design of a spacecraft and its mission. In the next section, we're going to discuss something that may be of particular interest to you. We're going to talk about how people live and work in space and how environmental hazards affect them.